So I need to hold this super close?
No, no,
This
I
is
think
fine?
it's fine. Yeah, yeah.
Okay.
And you just like you can just
Okay.
switch the slides with the
Okay.
keyboard. So now we have our second round of lightning talks, and we start with Kyra.
All right. So my name's Kyra. I'm a PhD student at Northwestern University, and my submission to the workshop was titled Task-Agnostic Safety Constrained Shared Control for Human Robot Systems. Shared control has shown great promise for different applications such as assisted surgery, search and rescue, physical assistance and rehabilitation, and many more. But how do we decide how to allocate control authority between agents, specifically between robotic agents versus human agents, especially in situations such as those listed? So there are many different things we can consider, from risk to safety to task-specific metrics. And many approaches currently in shared control research take the approach of task-specific metrics, and they try to determine which agent would provide the best control input to the system that does its best at achieving the specific task. But what if a task doesn't exist? So for instance, I'm holding a glass of water, and let's say it doesn't have a lid, but I'll keep it on because I have already spilled today. But let's say my only goal is to be safe, but I have a hot liquid. So the only thing that we're worried about is me not spilling the hot liquid. But maybe I want to walk around. Maybe I'm using an assistive device to do so. And I don't want it to interfere in how I'm walking about, because maybe I'm walking aimlessly. All I care about is it wants to help me not hurt myself with hot liquid. So for a shared control paradigm that does these types of things, we have three desired features that we're looking for. First of all, we want it to be constrained by safety, meaning that it's of utmost importance that we maintain safety the entire time. But we need it to be task agnostic. We do not want to have to define a specific task because the person doesn't necessarily have one. Or for instance, the task may be difficult to predict, and failure to predict the task successfully leads to a lot of frustration from the user. Additionally, we want it to intervene minimally. So meaning we want as much control authority to be allocated to the person as possible. So the main contribution of what I'm presenting today is a formulation for predicting safety over a receding horizon. And that's based on the human agent's current action, and it requires no knowledge of any explicit task or human intent. So for the robotic agent, in the following examples, I've decided to model them as model predictive controllers. And they have an objective that includes logarithmic barrier functions to incorporate safety constraints. So the main principle that we're trying to ask is, if the human agent's current action is sent to the system, can the robotic agent take over and prevent any safety violations from happening in the future? So to show you how this algorithm would work, I'll give you an example. So this is an example system that we have actually worked with before. We call it the ball and bowl system. It's meant to kind of mimic my glass of water, but instead you have a bowl with a ball rolling around inside and you don't want it to fall out. So it's modeled by a 2D pendulum that is positioned within a virtual bowl. And we can define safety of a system like this based on the angle of the pendulum, which corresponds to a maximum height of the ball. So this would typically be like the maximum height of the cup of water so that your water does not spill out. So the algorithm starts by measuring U desired, which is the human agent's desired input. It then forward predicts the evolution of the system for that single action for only a single time step, so the duration of only one single action. And then after that, the MPC takes over, and it uses an optimal controller to decide what it would do after that person's U desired is sent to the system. In this case, it predicts a safety violation, which in this case is being above, I believe that's pi over 2. And so it predicts a safety violation. If it does this, it will, instead of sending you desired, the human agent's desired input to the system, it will replace that with an optimal control from the same NPC. So here's an example of an entire trajectory. For this, the initial conditions, which you can kind of see over here, we're starting really close to the bounds, and we're also starting with an initial velocity. So it has plenty of energy that is going to allow it to oscillate above the desired angle. So you can see in the gray areas where it actually steps in. So it steps in early on to avoid the very first safety violation. And then as time goes on, it barely intervenes unless it gets close. So this is a good example here. Eventually it does get close and it intervenes again. And for the purposes of this, it's not a real person. I modeled the human agent as a PD controller with really, really large noise, so that it's just a terrible controller. So although this is exciting and promising that it worked on a virtual system, implementation on physical systems, especially those involving human-robot physical interaction, present different challenges. So not only can I just replace a numerical value in my simulation, now I have to forcefully counteract any actions from the person that are unsafe, or I have to replace them. So not only do I have to generate enough force to counteract, but also to add on top of that. Additionally, applications to real world and safety critical domains require further analysis of safety guarantees. And I think that's my time. All right.
Hello everyone, my name is Karan, and today I'll be presenting on how to synthesize high-level strategies for a robot operating in front of a human using the notion of regret. And I will then proceed to propose the notion of risk and how it can be incorporated using regret to strike a balance between performance and scalability. So robots are rapidly in their robot-centric environments, as you can see, and entering our society. So to be successful in their task, they need to have efficient interactions with the humans and also be able to perform complex tasks. For example, let's consider this scenario where there's a robot and a human operating in the shared workspace. The task for the robot is to accomplish the task, something while seeking cooperation with the human if possible, or build or accomplish the task on its own. So to incorporate such behaviors, we first specify the task using formal languages. We abstract the interaction between the robot and the human as a finite state machine. So this abstraction captures the evolution of the robot and the human as a two-player game. And finally, since this is a dynamic environment, computing a fixed set of actions is insufficient. So we aim to synthesize reactive strategies for the robot that reason and react to the human's actions in the workspace. So one line of previous work assumed the human to be adversarial and synthesize strategies for the robot. So while the robot guarantees task completion using this approach, the emergent behavior for the robot is very unintuitive. Another line of work proposes this notion of regret. So using this notion, we are able to synthesize more human-like or cooperation-seeking behavior for the robot, without assuming any prior knowledge about the human. And it also guarantees task completion. So what is regret? So informally, regret can be defined as the difference between, it's a quantitative measure of how good your action is. So for example, again, let's take the scenario on the top where the robot is tasked with building an arch with any 2 blocks of supports and green block on top. So the regret associated with this strategy of building the arch near the human would be higher if the robot knew beforehand that the human would intervene adversarially. So for the same strategy, the regret associated with this building the arch away from the human would be lower. Hence, we are trying to synthesize these regret minimizing strategies for the robot, which also allow the robot to seek cooperation. Mathematically, it can be defined as the difference between the current payoff associated with strategy sigma and tau, and the best alternate payoff associated with strategy sigma prime, as shown in the figure. So To prove the efficacy of these behaviors, let's consider two regions, a robot region where there is no human interaction and a human region where the robot and human can reach and manipulate the objects. And the task for the robot in this experiment is to place the objects in this configuration. So it's pretty simple. So for the regret minimizing strategies, we see that the robot first gives the human a chance to be collaborative, but the human intervene adversarially. But soon you will see that the human again open up a chance to be collaborative, and the robot takes this opportunity and says, sure, I can try accomplishing the task near the human, and finishes the task near the human. So while we are able to synthesize more like intuitive or human-like behaviors for the robot using this notion of regret, the underlying assumption that it has to complete the task is very conservative. So to relax this assumption, we propose to use the notion of risk and help scale up the algorithm. So let's take this abstraction over here. This abstraction is a two-player game that I mentioned before, and it captures the evolution of the robot and the human interacting. The square states belong to the system or the robot, and it has two actions to either go left or right, and the circle states belong to the environment, and it has two actions, either to intervene or not to intervene. So the dashed edge corresponds to intervening, and the solid edge corresponds to not intervening. So note that the robot takes an action, but it's up to the human to decide how the workspace or what the outcome of the robot is. So the leaf nodes that you see on the left and in the middle corresponds to completion of the task, while the leaf node on the right corresponds to partial completion of the task. So using the notion of regret that we saw a few slides ago, we can compute regret minimizing strategies, which in this case is to go left. That means that it's guaranteed to complete that task, but in that process, it has to spend either more energy if the human decides to intervene. So essentially, we compute these regret minimizing strategies that are finite memory or history dependent because it needs to take in the human's actions. But they scale up pretty badly. So using the epsilon regret, we as you see on the slides, we formulate this new notion where we relax this constraint. And going back to the same abstraction, we can see that if we fix the optimal strategies we saw a few slides ago and compute these epsilon regret minimizing strategy, the optimal strategy turns out to go right. So using this epsilon regret, we see that the robot now prefers to partially satisfy the task where it can guarantee that it's able to complete the task in 5 units. So we relax this completion, this constraint that the robot needs to complete the task, but also this also helps us algorithmically scale it up. So hence, in summary, we propose a new notion of epsilon regret by inducing risk into it, and we relax the winning strategy assumption. Thank you.
Thank you.
Hello, everyone. I'm Yiwei from Carnegie Mellon. I'm happy to present our work here today. So our work is essentially driven by this kind of a scenario where we have a multi-agent system, and the goal of the task of the agent A is to navigate safely to the target position while interacting with the other agent B, C, D safely. And all the agents share different personalities here. So there have been a lot of works addressing collision avoidance in this, addressing cross collision avoidance using methods like reciprocal velocity obstacles, buffer Voronoi cells, and safety barrier certificates. And usually the collision-free multi-agent behavior is modeled by characterizing the admissible control space or the collision-free position space for each of the robots. And it's commonly assumed that either all these interacting agents are fully cooperative in a symmetric manner or non-cooperative at all as moving obstacles. And usually the heterogeneity of these robots are characterized by various capability-related parameters like safety radius or actuation limit. So our goal here is could we reflect the different robots' intent into our safe control design? Yeah, and in the real world, it's highly possible that agent could, in the multi-agent system, can generate different reactive behavior in the collision avoidance scenario. For example, we have a bunch of delivery robots, and some of them are carrying goods with overnight shipping labels, and others are just having the normal ground shipping goods. So in that case, we will definitely want to have the robot with higher priority tasks to have the right of road. So our goal here is to first, we want to model the possible varying coordination levels in the agent collision avoidance behavior. And secondly, we want to design a decentralized control framework to accommodate the possible heterogeneity, which comes from the agent's different intent and to ensure interaction safety. And here by saying ensuring the safety, we mean to provide provably correct theoretical guarantees. So here's our problem statement. Basically, we have a number of agents, and each of the agents have their own global personality score, which reflect their intent. So the real question here is, how could we ensure this multi-agent system to be collision-free while taking these agent personalities into consideration? I think this is the old slide. Could we just refresh it?
Did you just change them?
Yes.
Okay. Okay, now you have to scroll.
This is the most.
Yeah, this one.
Right.
Yeah.
Maybe from this one.
This one.
Thank you. Right, so without diving into too much details, here's our proposed framework. So basically, this is the given information about global personalities of each agent. And next, we propose a concept called responsibility associated social value orientation, which comes from the social psychology concept, which measures the relative difference among agents between in such a pairwise agent collision avoidance scenario. And next, we propose the local pairwise responsibility weight, which could be understood as how much responsibility I'm going to take when I am interacting with another agent when we are doing the collision avoidance maneuver. And eventually, we present a decentralized control barrier function-based safe controller to take this intention into consideration to reflect this design idea. Yeah, so here are some quick examples. The first is on two agent position swapping games. And these three different columns represent different agent settings. Like this one is, the first agent is egoistic versus altruistic agent. And this here, we have both of the agent as pro-social. So here we can see our proposed method is able to achieve different levels of coordination. And second example is on the self-driving car is in freeway ramp merging scenario, where the initial condition we set both of the vehicle has the same same distance from the merging point. And in the case one, we can see if both of them have the same personality, then the deadlock situation will happen, which is exactly what we are expecting. And in the second case, if we have the first vehicle as the egoistic one and the second vehicle as the altruistic one, we can see the first vehicle will get the right of road and get to the merging point first. And in the third case, when we have the second vehicle as more egoistic than the first vehicle, then in this case, the first vehicle will going to yield to the second one. So we can see the safe behavior generated by our proposed controller is well aligned with the agent's social preferences or personalities. And the last case is on the multi-agent position swapping game, where we have 6 robots, and the task is for them to switch positions with each other. And we have agent 135 as altruistic agent and agent 246 as egoistic agent. So the first thing is we can see we have the symmetric coordination as baseline on the left, and we have our proposed asymmetric coordination on the right. And the first thing is our proposed method is achieving a higher task efficiency by completing this task quickly. And second thing is during this deadlock resolution phase, our proposed method, instead of forming a circle around the center, it is forming like 2 triangles around the center. So the inner triangle is formed by the egoistic agent, which means they are having less deviation from the nominal task. And the outer triangle is formed by the altruistic agent, which are willing to travel longer distance. So from this perspective, it's kind of a trade-off balance between the travel distance and the task evasion. Yeah, so with that, I would like to stop here. You can scan the QR code for our full paper, that's my email up there, and I will be happy to take any questions later. Thank you.
Hi, everyone. My name is Rebecca Martin. I'm from Carnegie Mellon University, and my project is on risk-aware collision avoidance for multi-drone cinematography. So when I say cinematography, I'm referring to general filming applications and not just in the making of movies. But when we start out, if you look at a movie and you see like a dangerous stunt being done, often we think about, oh, how dangerous is that for the actor or the stunt double? But we don't always think about the camera crew. And some of these stunts require dangerous locations, hard to reach angles. And it's also more dangerous because the camera crew has all this equipment. And one solution for this is we can use drones autonomously to film these. Like I mentioned earlier, filming can be for a variety of purposes, depending on what's being filmed and for what. So we would need to take different things into account if we're filming humans or animals and for what purpose. So in our project, we're looking at filming for 3D reconstruction. We want to build a system that is going to detect and track actors. Here, when we say actors, this is just the people being filmed, not necessarily professional actors. And we want to do it such that we optimize for this filming objective. So, like I said, for 3D reconstruction, we want to maximize the coverage of our actors, and we also want multiple viewpoints. And we're also doing this in unknown environments with a variety of obstacles. So this always comes with inherent risks, the most important being safety. Of course, while we need to follow the actors from a certain distance for good resolution, we also want to ensure that there's going to be no collisions for the actors, for the people in the other people in the environment, and for any obstacles. Of course, we also have task failure, which could be not getting a good enough coverage or accidentally losing the actor from the frame. But we're going to focus on safety. Oh no. So previous work focused on tracking. It's not the
No, it's very tough to give accents, but I think now I don't know if you have your phone, you could try. But
no, we can move on. It's
Okay.
because it's not on my drive.
oh,
It's on the lab drive. So I had an image that showed a person walking through the snow, and it showed two drones following them. And as the person walked by a mountain, it showed how the drones turned to avoid the obstacle. So that's our current work. We have previously done in my lab. We have a system that can detect and follow a person in a known environment with minimal obstacles. So now we want to add in what happens if there are people around. So our goal is to build an autonomous trajectory planner. And the way we are going to incorporate safety into this is by setting a minimum allowable distance. So even though we need to follow close enough to the actor, there needs to be a certain distance for safety. And for the obstacles in the environment, whether it's static or dynamic, a static obstacle would have a fixed allowable distance, whereas the dynamic obstacles, it can change over time. So that's where we take into account relative speed and position. If a dynamic obstacle is moving slowly, or if it's not going to cross paths with the people being filmed, then that would give it a generally low risk. Whereas if it's going at fast speeds, or if it's going to go and intersect paths with the actors being filmed, then that's going to be a higher risk. Of course, every system needs a fail-safe. Currently, we're using safety pilots, but in the future, we are going to incorporate an autonomous fail-safe. So in conclusion, autonomous tracking and filming can solve many of the current challenges in cinematography. And once we finish the system, we'll evaluate it in a photorealistic simulation environment and test in real world scenarios. Thank you.
Thank you to all of the speakers of this Lightning Talk session. So do you have any questions? Yes.
Yeah, so for the photorealistic, are you using AirSim? Okay. And I have another question for the previous speaker, if I
Yes.
may. No, the one right
Okay.
before.
Question for you.
So how did you infer the SVO? Well, the new version of the social value orientation, how did you infer the values of the other agents? Did that came from the observations? Or did your agent knew the social value orientation of the other agents? Or how did it estimate it?
So let me repeat the question first. The question is, how do we know the information about social value orientation of each agent, right?
Yeah, of the
Okay.
other ones than the one that you're controlling.
Yeah, so that's a good question. So in our paper, would you mind to go back to the overview slide? Yeah, here. So here is the place where we calculate our relative social value orientation. And this is given the information of this global personality scores. So basically we know how each agent is like whether it's globally egoistic or whether it's globally altruistic. So this information is given. So what we do is we want to embed this information into our safe controller design to reflect this heterogeneity instead of being modeled by the different controllers. We want to reflect this information. So basically we know how the agents are like by personalities, and we want to control let them to generate different kind of behaviors. So this is what we know, and this is what we do.
Okay.
Yeah,
thanks.
does that answer your question?
Yes, thank you.
Nice.
Any other question? Is there a question in the chat maybe?
So I have another question if there are no questions. So
Yeah.
for the one with the drone, so for you, how did you get the difference? So you mentioned the risk of like crossing the path in front of a person and so on. Were those risks defined by hand, or how do you get those different risky situations?
So first, we have a prediction based on the current velocity of each of the moving obstacles. And for now, we are going to.
Okay, thanks.
Okay. So okay, we have okay, thank you. We have another set of speakers now. So maybe